Oh, it's about time, so I guess we should go ahead and get started. See, I got Chloe and Zach here. You're welcome to go ahead and chat me your first and last name if you haven't done so already. We are going ahead with chapter 10. I have some examples that we're going to work in throughout there. I wanted to let you know I decided to push the date back on the face or the online test that was due. It was originally due like Sunday for you guys, but then I moved it to like Tuesday and then Wednesday. Well, I just went ahead and moved it to Friday. So, so that online test actually has a date of Friday. If you've done it already, that's great. It's no big deal. It's just I gave you some more time to do it. And the reason specifically was my plan was to go ahead and have a face-to-face test Wednesday for my for my face-to-face students, and of course anybody else that wanted to show up for that test could be tested at that time as well. Uh, but I haven't covered as much material as I'd really like, so I've decided to move that online, or excuse me, that face-to-face test to Monday, the 28th. That means you guys will have all day the 28th where you can come in to take that test with me as a proctor, or you can just uh, find a time that the proctoring or that the testing center on your nearest campus can do it, or you have to find some other way of getting it proctored. So just remember that that's the deal. What I'm going to give you guys, since your online class, is I'm basically just going to say the test will not necessarily come out as a face-to-face test until Wednesday of this week, but I'll leave it up until Friday of next week, I guess. That will be the face-to-face test that you have to have proctored. There's probably going to be another online test, but that one doesn't require a proctor or anything, so that's not that big a deal. And then the original date for the final was the 30th, which would be a week from Wednesday. And you're still welcome to take your final at that time using me as a proctor, but you're not required to. I will allow you to take it as late as long as you finish by 2 p.m. on Monday, the 5th. So you have the option of taking the final exam on Wednesday, the 30th, uh, at any time during, well, actually, any time with me if you want me as a proctor, but you also have all the proctoring schedule that the various testing center has for all the campuses. But you can also take it again Monday as well. Monday's the latest it can be taken, and it has to be done by 2 p.m. on Monday. Again, that's not a week from today. That's 2 weeks from today. So y'all can rewind this video once it's posted if you have any questions about that. I'll also be sending out some emails to let you know what's going on with that. In your case, what I'm trying to do is I want to include chapter 10 and ideally chapter 11 on the next face-to-face test. So it all depends on what I can do today regarding chapter 10 and then with my online videos that I'll post for you guys. So as you saw, I posted several videos this weekend. There'll be some more posting as well tomorrow, maybe some more Wednesday, and maybe some more Thursday. And then, like I said, ideally the test would be covering chapters all the way through 11 on that. Now, the remaining material of the semester is just chapters 14 and 15. So automatically, any homeworks that are outside of the chapters 1 through 11 and 14 and 15, any chapters that aren't those numbers, they're considered extra credit, whether they're marked extra credit or not. So they're just counting as help for you guys. Make sure you do that if you feel like you need the extra credit. That's a good thing to do. But the main thing is just know that they're not all the other ones aren't required. That being said, I may or may not be able to justify requiring you to turn in chapter 14 and 15 homework. So that might actually turn into extra credit as well. It all depends if I can get chapters 14 and 15 videos online to my satisfaction by Monday. If I can, then I don't mind it. But if I don't, then we're going to make chapters 14 and 15 extra credit. But you will be tested on them. I'm just saying I'm making the homework extra credit, but you will be tested on them on not the final face-to-face test, but on the final exam and probably on the next online test if we have that one. So those are my big announcements. for the internet class as well as for my face-to-face class. I've gotten three people already chatted me your first and last name, so feel free to go ahead and chat me your first and last name if you haven't done so yet. I'm going to go ahead and turn on my iPad screen so you guys can see what I'm going for. We're in chapter 10. Like I said, my ideal scenario is I finish chapter 10 today and maybe go into chapter 11. But either way, I'm definitely going to immediately start tonight, tomorrow, Wednesday, as well as Thursday. I'm going to immediately start making a series of videos on the critical stuff for chapters 11, 14, and 15. Okay, that means I'm not covering all the depth of chapters 14 and 15, and maybe not even chapter 11 that much either. But the main thing is the stuff that I show you, you're certainly responsible for on the test. And if I skip any sections, I'll tell you what sections of the book I'm skipping. The other sections, you should just know how to do those examples in the book, and that should be more than enough to help you. So let's go ahead and get started. I'm going to share my screen. Anybody have any questions before we do get started? Okay, I know I'm probably inducing a little bit of anxiety for you folks with the way this is going. So just be advised, I'm never going to be unfair to my students. And actually, I don't know what's going on right now, but it's not acting like it wants to pair. Let me stop sharing real quick and try it again. I want to let you know I'm never going to be unfair to my students. So if I look and it looks like what I've done has made it unreasonably difficult for my students to succeed, then I'm going to throw out the part of the questions that came from the most recent stuff. In other words, if my 14, 15, and maybe even chapter 11, if that material is a wash, meaning that literally everybody in the class does horribly on it, then I will be required to look at it and decide whether I'm going to throw that out completely because of the way I had to cover it this time. So just keep that in mind. I'm not going to let you guys. I'm not going to stiff you guys by giving you something that you haven't covered well enough and that sort of thing. So just keep that in mind. I got you back. I'm going to take care of you. Let's go ahead and get started with this example. You'll notice this is just like an example from chapter 10, but again, I've changed the details of it in hopes that I'm not violating any copyright. Example 1, two small weights are mounted on a 1.00 meter long, thin, light balsa wood rod. So all of that is an attempt for me to tell you, hey, we're not going to count the balsa wood rod, okay? One mass is 6.00 kilograms and is centered at the end of the rod. The other is 4.00 kilogram mass and is 50.0 centimeters from the other mass. A, what is the moment of inertia of this arrangement when it is rotated halfway between the two masses? And B, what is the moment of inertia when the rod is rotated about the end opposite the 6 kilogram mass? You can ignore the mass of the balsa rod. So, what I'm going to do here is solution, and that's normally where I list some facts that I know. So I'm going to say M1 equals 6.00 kilograms. I'm going to say uh, X1 is going to be at the very end, so that's 1.00 meters. M2 is going to be 4.00 kilograms, and X2 is going to be at, I said 50 centimeters, so that's going to be 50.0 centimeters. Again, using some, in some sense, the end as like an origin of the coordinates. Uh, and that's pretty much it. Now I'm going to draw a diagram of what we're looking at. And basically what we should have is a uniform rod that is thin and light and happens to have a mass about zero. In other words, very, very small. Now, in addition to that, we have a mass on this end, which is M1 equals 6.00 kilograms. And then at the other end, I'm going to imagine this is like a Y or like an X axis along here. So I'm going to draw a line right through the middle and call this X. And I'll call this X1 equals 1.00 meters. Now I'm going to go over to here and the other mass is 50 centimeters from the center. So I'm going to go right about here and say this is x2 equals 50.0 centimeters. And halfway between them will be the axis. So halfway between 50 and 1 meter, 50 centimeters and 1 meter is 0.75. So I'm imagining the rotation axis as if it is right here. And that corresponds to x, uh, I'll say XA because this is the rotation axis for part A. That's going to be 0, or let's say that's going to be 75.0 centimeters, like that. And now that should be good enough. Now we can go ahead and use our equation, which I haven't given yet, but the equation we have is I equals the summation from I equals 1 to N of M sub I R sub I squared, where R sub I is the distance from the rotation axis perpendicularly to the center of mass of the individual objects. I did draw one of the masses. I haven't drawn the other one. I don't know why. I sort of got obviously a little bit discombobulated or something. But the other mass goes right here, and evidently it thought that was closer to a uh, square than a circle, so that's not good. And it thought the same thing with that one. Let's try again. There you go. And this one is M2 equals 4.00 kilograms. Okay, so for part A, we're going to go ahead and say I is equal to, in the first case, I have the 6.00 kilograms. Now we see the rotation axis is actually 0.75 meters, and the end for x1 is at 1 meter. So the difference between those is 0.25 centimeter or 0.25 meters. So I'm going to go ahead and write 0.250 meters squared. That represents our r squared. Plus, I have on the other side, again, another 25 centimeters away, but this time the mass is only 4.00 kilograms times 0.250 meters squared. So we can go ahead and calculate this as follows. It's 6 times 0.25 squared plus let's do 4 times 0.25 squared. 4 times 0.25 squared. That gives me 0.25, and the 6 times 0.25 squared gave me 0.375. So this is 0.375. All three of those are significant figures, plus 0.250. And the units, of course, are in kilograms meters squared, like that. So I'm going to finally write I as, I can add those two together, and we see that it's good to three sig figs, and therefore three decimal places in this case, because both of them were three sig figs, and both of them were carried out to three decimal places. So this is 0.625 kilograms times meter squared is the moment of inertia about the axis dead center between them. Now I can do the same thing for the other axis, and the other axis I'll also write in green, and that's going to be right here. So this is x sub b is equal to 0.000 centimeters, for instance, or we could say actual meters would have been good there. Either way, it's good. So now we're going to take part B. Anybody have any questions on that part A before I go on to part B? Okay. So I is still the same formula, but this time we have the 6.00 kilograms is actually an entire meter away. So that's going to be 1.00 meters squared. And then the 4 kilograms is actually half a meter away. So that's going to be 4.00 kilograms times 0.500 meters squared. And that's going to be our moment of inertia as rotated this way. So I can clearly see that this is going to be 6.00 kilograms meter squared for the first term. And then for the second term, it's going to be zero point 0.5 times zero point 0.5, which is 0.25, and then times 4, which is 0.25 is 1/4. So that's going to be plus 1. So this is going to be 1.00 kilograms meter squared. So in this case, we get I is equal to 7.00 kilograms meter squared for the moment of inertia for part B. Anybody have any questions on that? All right. Hopefully you guys saw the videos I made this weekend. I just want to remind you, make sure you check those out. There's 3 or 4 of them I put up there. I definitely recommend you subscribing to my YouTube channel at least long enough to get through the semester, because I'll be posting a lot of videos trying to help you guys or help us catch up. And I apologize for doing that to you guys. I know, I'm obviously partly to blame, if not majorly to blame. But like I said, I just have a few minimums that I want to get you through to make sure y'all can function at the next level. So the real critical thing is some key parts of chapters 14 and 15, and a little bit of chapters 10 and 11. Let's go to the next example, example 2. This says a constant 17.0 Newton force is applied as a tension on a rope that is essentially massless and is wrapped around a 3 kilogram pulley of radius R0 equals 0.333 meters. The pulley, starting from rest, reaches an angular speed of 24.0 radians per second after its 3.00 second long uniform acceleration. Assuming a frictional torque of 0.875 meter newtons, what is the pulley moment of inertia? So, what's the pulley's moment of inertia? So, in this case, we're actually using a pulley and we're going to apply Newton's second law in the rotational form. So, I'm going to start off with solution, as always, and I'm going to record the information. I've got a force that's acting as a tension is 17.0 newtons. I got a friction torque, so I'm going to call this torque due to friction is equal to 0.875 meter newtons. Now, I'm not putting a sign on that, but just remember that friction in some sense impedes motion. So as soon as we figure out which direction the pulley should be rotating, the torque that's due to friction will be a rotation, will tend to cause a rotation in the opposite direction. So that will dictate whether we get a negative or a positive, that sort of thing. We also know that omega zero is 0 and omega final is 24.0 radians per second. And delta t, the time elapsed, which is t minus t0, is evidently 3.00 seconds. And we have r0 is 0.333 meters, which is really as close as we're going to get to 1/3 as we could. So what we want to know, like I said, is I for the pulley. and that's the question mark. I did also have a mass for the pulley, just like the radius for the pulley, and the mass for the pulley is 3.00 kilograms. Now, the equations we can use, for instance, are the summation of the torques is equal to I times alpha. Now, that's only true if alpha can happen to turn out to be a constant. If it doesn't turn out to be a constant, then it also could be the summation of the torques is equal to I times d omega over dt, and then you have to solve it like a differential equation, that sort of thing. We're shooting for alpha being a constant. We can also use alpha as an average formula is omega minus omega 0 over t minus t 0, and we almost always just assume t 0 equals 0, uh, which I can put right there as well. So now that I have all that, I can go ahead and draw my diagram. First off, I want to draw a pulley. So there's my pulley. It has a radius R0. It has a mass 3.00 kilograms. And what it has acting on it is a force that is a constant force. We're calling that F tension equals 17.0 newtons. And that is essentially our free body diagram because it's literally the only thing acting on it. Obviously, you have a force of gravity. Excuse me. Obviously, you have a force of gravity that's acting on the pulley, but that's going to be exactly counteracted by the normal force acting on the pulley. So I don't really need to show those. We also have a drawing here that suggests this tension in the rope that's 17 newtons. That's going to tend to rotate this pulley in a counterclockwise direction. So I can also say that we have a clockwise torque that is T friction, and that one should be, if I use my normal sign convention, which I often use, which is X, Y, and torque is that way, then the torque due to friction is a clockwise friction torque, so it's going to be a negative 0.875 meters times newtons. So we can use that. Now I'm going to take the summation of the torques is equal to I times alpha. That's the equation I want to use, but first off, I'm going to find out what alpha is. Alpha on average should be 24.0 radians per second minus 0, and then all that's going to be divided by 3.00 seconds. You can see that 24 divided by 3 is 8, so this is going to be 8.00 radians per second every second. I'm going to go on the assumption that that is a uniform acceleration. And in fact, looking at it, since we have the torque as a constant due to friction, and we have the torque related to a constant force, 17 newtons, times a constant radius, R0, that tells me that the two forces on the left-hand side are a constant. Therefore, the moment of inertia and the A alpha should also be constants. So, or at least they would have like reciprocal sort of dependence so that one cancels out the other to make the right-hand side be a constant, just like the left-hand side. All right. So
Why
now that
is
we have
the
that, go ahead.
torque of friction
Hmm.
in the clockwise direction?
Yes. What about it?
Why is that?
Okay. So what we have here is a force that's going to be constant. They're trying to stress that this is not a hanging mass, and since the if it was a hanging mass, then the force wouldn't be a full 17 newtons on it because it's falling. But this one's going to maintain a constant 17 newton force. But because that force is acting on the left hand side, that tends to rotate the pulley counterclockwise. And friction always acts to impede the motion, so the friction should be acting in a clockwise direction. So me calling counterclockwise a positive torque means I have to call a clockwise torque a negative. Does that make sense?
Yeah, thank you.
No problem. Yep. All right, so let's go ahead. I think we can see, remember torque, and I did several videos on torque this weekend too. Torque has a couple different formulas. As a vector, you can say it's R cross F, and then you can say its magnitude, torque, is equal to R times F times the sine of the angle between the lever arm vector R and the force vector F when they're tail to tail. But you can also say that that is the component of the lever arm perpendicular to the force times the entire force. Or you can say it's the component of the force perpendicular to the lever arm times the entire lever arm. So those are like three different ways we can actually calculate torque. What we're going to see is the torque due to the friction, due to the constant force is, notice that's a 90-degree angle. That little blue vector is the lever arm. Therefore, we can say that the torque due to the friction force, or excuse me, due to the constant force is 17. Oops, I should delete all that because it's on that automatic make it better drawing thing. So I'm going to say the radius is 0.33 meters. The force is 17.0 newtons, and that's a positive torque because it's causing a counterclockwise rotation, minus 0.875 meter newtons is equal to I times 8.00 radians per second, like that. So if I multiply 17 times 0.333, I get 5.661. Now notice that was 3 sig figs and 3 sig figs. So this 1 and the 0 are not significant figures, and that's meters times newtons minus 0.875 meters times newtons. Notice the 0.875 is good to three decimal places, but the 5.66 is only good to two. So when I add these two, it's only going to be good to two decimal places. And I've got I times 8.00 radians per second, which you can call radians per second squared, but I rather say it radians per second per second. So if I take 5.661 and subtract from it 0.875, then that's going to give me 4.78. And then the next digit is 6, and the next digit is 0, and they're not significant, but that's the total torque on the left-hand side, and that's equal to I times 8.00 radians per second every second. So now I can say I is going to be that 4.786 divided by 8. So this gives me I is equal to 0.598. I am dividing 3 sig figs by 3 sig figs, so I should be able to get 3 sig figs out of this. But I'm adding these extra two like I always do, and this is kilograms times meters squared. And that should be the moment of inertia. Now, if this were actually a cylinder with a radius of 0.33 and a mass of 3.0, if it was just a pure cylinder, the moment of inertia would be 1/2 m r squared. So just ballpark figure, let's see how well this compares and see what we'd have to do to make it fit reality. In other words, to figure out what has been done to this pulley that would make it significantly different from a just a regular uniformly distributed mass cylinder. So this is 1/2 times 3.00 kilograms times 0.333 meters, and that's going to be squared. So zero point 0.5 times 3 times 0.333 squared gives me a buttload smaller quantity, 0.166 kilograms meters squared. So obviously this is much, much larger moment of inertia than much more of a moment of inertia than we would have had for a typical just cylinder. My guess would be that as a pulley, it probably might have a very thin webbing type material between the rotation axis and the part where the U-shaped gunnel, if you will, where the actual rope goes through, and then that actual rope part might actually be pretty significantly heavy and made of thick material. That would account for a lot of it because remember, it's not only the mass, it's the square of the radius. So if you go out on the outer edges and put a lot of mass, you're going to get a lot bigger effect. So this is at least the same ballpark, but much, much, much smaller than just or I should say, the moment of inertia of the cylinder is much, much smaller than the moment of inertia of this particular pulley. I think that's it. Yeah, that's the only thing regarding this question. I even did the extra part myself. So let's try another one. But first, I want to see, does anybody have any questions on this? Okay, it looks like you guys are good. Let me go ahead and put my chat up there. I did tell everyone to go ahead and chat me your first and last name. If you haven't already done that, please do. It looks like everybody has. And I just checked to see if anybody had sent any other messages. I don't see any other chats to me. So let's start with our example three. This one says a 1.73 kilogram bucket hangs from a massless rope wrapped around the pulley from the previous example. So in other words, we're actually using the same data from the previous uh, uh, example. The friction is not changed either. Assuming the rope does not stretch or become slack, calculate the angular acceleration of the pulley, alpha, and the linear acceleration, a, of the bucket. So that's what we're going to do. I'm going to go ahead and record some information that we'll need. Whoa, Nelly. Solution. Okay. So in this case, we have the hanging mass, which I'll say M sub B for the bucket, is 1.73 kilograms. That also means that MB times G, which is the weight of the bucket, that's going to be 17.0 newtons. It actually works out to be 16.953 or 958 or something like that, which obviously rounds to 17.0. That's what I'm doing. And you can notice that in this case, it's actually a bucket hanging and it will be falling. So unlike the last one where the accelerate or where the force was a constant on it, in this case, the force is not necessarily going to be a constant. It's not going to be 17 newtons. Okay. We also know that the mass of the pulley is equal to 3.00 kilograms. We know that the radius of the pulley R0 is 0.333 meters. And that's pretty much it. The rope is massless and so on. So, what I'm going to do now is I'm going to draw a diagram of the system. So, there's my R0 right there. And now over on this side, I have a tension T acting this way. I also have because the tension tends to pull it in a clockwise direction, I can now say that the torque due to the friction is also 0.875 meter newtons. And I made it negative because obviously it's going in the opposite direction. Okay. Now, in addition to that, I've got a free body diagram for the hanging mass. I should draw that in blue. So the hanging mass, I have a 1.73 kilogram mass here. it has a weight W equals 17.0 newtons acting this way, but it also has a tension T acting this way. And I'm going to consider this as the positive y axis. Okay. Just because that is the direction that the W, the bucket, should be going, and therefore the acceleration will come out positive. I've got the free body diagram for the pulley, and I've got the free body diagram for the hanging mass. So first off, I'm going to say the summation of the torques is equal to I times alpha. That's going to give me basically 0.333 times the tension. And I'll leave off the unit, but you recognize that that should be in meters. So that times the tension, because they are perpendicular, minus the 0.875. I'll leave off the units here too. Is equal to I, which we determined was 0.598. So 0.598 kilograms meters squared. And all of a sudden, I'm including the units for some reason. Okay. That'll allow us to solve for alpha, which is one of the things we want to know. I'm going to call this equation one. Now I'm going to take the summation of the forces in the y direction equals mass times acceleration in the y direction. And that is for the hanging mass diagram. So in this case, I'm going to get 17.0 newtons minus the tension T is equal to 1.73 kilograms times A. And that's going to be equation two. So the first thing I'm going to do is divide through by 0.33 on equation one. I think that'll be nice. And then I'm going to, actually, no, Artem, I don't think I want to do it that way, but I could do R times alpha. Oh, okay. All right, what I'm going to do is multiply equation 1 by 0.33. Now, this is completely arbitrary. I'm just looking for neat and easy ways to get out answers that look really nice. So I'm going to multiply the whole thing by 0.333 meters. And I'm going to do the same thing for equation 2, only I'm going to multiply it by 0.33 meters squared. So times 0.333 meters, but now I'm going to square that one. And that'll give me a new equation 1 prime. And 1 prime becomes 0.333 times 0.333 is 0.11089. So 0.11089 meters squared T. Now I'm putting the unit back in because it's getting nasty. Now I'm going to take the 0.333 times 0.875, and that gives me 0.291. And keeping two extra sig figs, that's going to be 38. Keeping two extra digits. And that actually turns out to be, since the 0.875 was already in meter newtons, now I've got meters squared times newtons. And that's okay. That's completely consistent with the unit that I have in the term right next to it. And then I also have 0.598 times 0.333. And that gives me oops, that gives me 0.199 Carrying two extra digits will be a 1 and a 3. And that figure comes out to be in kilogram meters cubed times alpha. Okay, so that's what happened when we multiplied equation 1 by 0.333 meters. Now we're going to take equation 2 and multiply it by 0.333 meters in parentheses squared, and that's going to make equation 2 prime. So I'm going to put a 2 prime right here, and I can take 17 and multiply it by 0.333 squared, and that gives me 1 point, oops, I'm writing a little higher than I meant to. That gives me 1.88 51. And notice the unit before was just a Newton, so now it's a meter squared times a Newton. So meter squared Newton. Now the other one is just the tension. So 0.333 squared becomes, I think that's the 1108. Yeah, that's it. So this one, this second term, the T, is going to become 0.11089, and that is meters squared times T. And then on the right hand side, I've got 1.73 times 0.333 squared, 1.73 times 0.333, and I square that. That gives me 0.191, and then two extra digits would be 84. And that was just kilograms. Now it's meters squared times kilograms times A. Okay, so now we have equation uh, 1 prime and 2 prime, and I can add them just like we normally do with the Atwood machine, even though this isn't an Atwood machine. But because we have that tension and the other tension having equal but opposite coefficients, then we can just add them, and the tension, which is one of the unknowns, will disappear. The other thing we can do is, since this rope does not get slack and it's not going to slide, then it turns out that the equation S equals R times theta applies. What I mean by that is, if I pull the string that was holding the bucket, if I pull it down exactly 1 inch, exactly 1 inch of the circumference of the pulley will move as well. And in fact, if I did that in 1 second, the same thing would happen in 1 second. That shows in the first case that the arc length is exactly equal to the string length, and that's exactly equal to r times theta. In the second case, we're saying V is equal to R times omega. And then if we also consider doing that, maybe making it move 1 meter in 1 second, or excuse me, 1 inch in 1 second, and then after another second, make it move 2 inches in 1 second, then that's a type of acceleration, and we'd get A equals R times alpha. So as long as it's not slack, or I'll say without slipping and no slack or stretchy strings, then we get S is equal to R times theta, which we can take the derivative with respect to time on both sides, realizing R is a constant, and we'll get V is equal to R times omega. And if we take the derivative of both sides of that with respect to time, realizing R is a constant, we get A is equal to R times alpha. These conditions are automatically true if it slides without slipping, and you need to make sure the rope's not getting slack or stretching because that sort of does the same thing. But as long as none of that's happening, then we have this nice relationship between alpha and R. And in fact, I can go ahead and replace, or excuse me, between alpha and A. In fact, I can go ahead and factor out a 0.333, for instance, from equation 1 prime on the right hand side, and that would generate R times alpha, which is the same thing as A. So I can take 1 prime and make it 1 double prime by saying 0.11089. I forgot to underline those before. Meter squared T minus 0.29138 meter squared newtons is equal to, now I'm going to take the 0.19913, and what I'm going to do is realize that I got to pull a 0.333 out of that. So in order to do that, I've got to divide it by 0.333. So this ends up becoming 0.597, and then two extra digits would be 99. And since I actually canceled out, let me make sure I took the right one. 19913. Yeah, I just want to make sure I didn't accidentally grab the right hand side of 2 prime. So what I did was I took 19913 and I divided it by 0.333 and I got 0.59799. And notice that was kilograms meter cube, but I just factored out a meter. So now I've got kilograms meter squared. And by dividing out that 0.333, I can now multiply the alpha times 0.333 and it becomes A. So everybody follow what I did there? It's tricky math that I just did because I knew I could. You can do any other way. Don't worry about if this idea never would have came to you. That's okay. It's just what I chose to do. Okay. Now that I have that, I can go ahead and consider adding the two equations. So I'm going to add these two. So what's going to happen is I get the 0.11089 meters squared T minus 0.11089 meters squared T. Those two are going to completely cancel out. But what I do get to keep is 1.8851 meters squared Newton minus 0.29138 meters squared newtons. So now what I see is I've taken care of that term, I've taken care of that term, I've taken care of that term, and I've taken care of that term. So now I've gotten everything from the left-hand side. Now I'm going to say equals. Now on the right-hand side, we have two things, both of which are being multiplied by A. So all I have to do is add those two. That's 0.19184 plus 0.59799. That gives me 0.78983 kilograms meters squared times A. Okay. Now you can see I just have basic arithmetic with a little bit of algebra where I'm going to have to divide both sides by 0.78 78983. So I'm going to do that now, dividing both sides by 0.78983 kilograms meters squared. And then I'm going to do the same thing over here, 0.78983 kilograms meters squared. What I can see is the 1.8851 minus 0.29138 0.138 gives me 0.15937. So I'm going to write that right above it here. This is 1.59. This is actually good to two decimal places, so I'm good up there. And then this would be a 3 and a 7 meters squared times Newton. So that's the result of subtraction. Now I got to divide that by 0.78983. That gives me on the left hand side 2.01. Now we are dividing 3 sig figs by 3 sig figs, so we get 3 sig figs. 2.01 is all of them. So now I can include a 7, which isn't significant, and then an 8, which isn't significant either. But that gives me two extra digits, and that's meters squared newtons. And the right hand side is just equal to A. So what I've figured out is the acceleration of the bucket is 2.02 roughly. And now I can use that to figure out what alpha is. And alpha, of course, from A equals, actually, let me write that in blue. From A equals R times alpha, we know that alpha is equal to A over R. So it's 2.0178 with the 7 and 8 not actually being uh, significant, and then dividing this by 0.333 meters. By the way, 1 Newton is equal to 1 kilogram meter per second squared. So when I multiply by meters, oh, I forgot to do the other part. That's why. I was worried about the units. I just blindly wrote down meters squared per second. I don't even know why I blindly wrote that down, but it's meters squared newtons divided by kilograms meters squared, which actually makes it make a lot more sense. So I'll say divided by kilograms meters squared. You can see that this meter squared cancels out with that. And the Newton, which remember is a kilogram meter per second squared, if I divide that by kilograms, I just get meters per second, which is exactly the units that we want. So we can say it's 2.0178 meters per second per second. Sorry about that. I wasn't even paying attention to the units when I did it, but I wanted to make sure I got it right for you guys. Now I'm taking this 2.0178. I'm going to go ahead and use the appropriate units that we just worked out. So that is uh, meters per second every second. Whoa. So that's meters per second. Now, when we divide that by meters, that ends up giving us nothing per second, which we can obviously make into radians. So I'm going to take this 2.017 and I'm going to divide it by 0.333, which is more or less the same thing as multiplying by 3. And we get equals 6.05. That's my 3 sig figs. And then I have a 9 that's not significant and a 5 that's not significant, and that is in radians per second. And I don't know why my 5 is written up there high like that, but I'll fix it. All right. Anybody have any questions on that one? So yeah, that does say newtons per kilogram in the units for A, but that's the same thing as meters per second per second. But now you know exactly how it worked out and all that good stuff. Anybody have any questions on that one? All right, and it looks like no one had any more chats. So I'm going to continue on. And specifically, we've sort of now worked a major type of problem. What I wanted you to see is even though both of them had 17 newtons hanging on it, that was an entirely different scenario. When we did the 17 newtons earlier, that was a constant force of 17 newtons. In this case, the 17 newtons is what would have to be applied as tension if it were to hold it still. So it's actually a little bit less than 17 newtons, and you get a significantly different result. For instance, in this case, we get 2.01 meters per second, and with the other one, we ended up getting eight. Oh, no, that was radians. We ended up getting. Oh, yeah, that's right. We actually worked it out to be A is equal to R times alpha, and R is 0.333. So R times alpha would make this into a third of 8, which would be 2.67. So the acceleration there was about 2.67. The acceleration here is about 2.01. That's somewhat reasonable. We expect it to be a little bit less because it's not actual 17 Newton force. Any questions on that? All right. Now there's a rotating rod problem. Ooh, I don't even know how this got here. This one's not necessary to be here. This is actually from one of the torque problems that I work, or shoot, yeah, one of the torque problems I worked this weekend. I actually went through and did this problem for you guys. There is a mistake though, and it's right here. So when you do watch it, and I put a note on it on my YouTube channel, but basically what this was supposed to do was give a negative 250 minus a negative, which would be a positive one, which would basically subtract from each other. But what actually happened was I got this answer, this 28.68, when it was supposed to be negative 67.36 Newton meters. So just keep that in mind because I do tell you in the notes, but it's just simply a single misreading, or you might even call it a typo mistake. So now I'm getting rid of that. Now I'm gonna get rid of the other one too. Okay. Now the next example I want to do is one where we're going to work on a rod that's just going to fall. So what I have here, let me draw a picture and then we'll figure out how to go about wording it and all that good stuff. But basically, what we have is a wall, and attached on this wall is a little axle. And then attached on this axle, and I mean really, really small. I'm drawing it so you can see what it is, but in reality, it would be really, really small compared to the dimensions of the actual beam. So the beam is like this. And let's say this beam has a mass of big M, and let's say this beam has a length L. Okay. In other words, I'm completely ignoring this little space right here. Ignore that space. I'm just showing you so you know what's actually going on there. And in fact, it probably would be better if I put the hinge right here on the bottom so that this little corner right here doesn't hit the wall when it's coming in. But I just wanted to show you it's hinged. So we're going to ignore this little distance, which I'm going to say is on the order of 1 times 10 to the negative third meters. So, in other words, it's on the order of a millimeter instead of a whole meter or a centimeter or anything like that. So, it should be insignificant, in other words. Okay. Now, that's that. It's a uniform rod, and because it's a uniform rod, that also tells us that the distance from here to the center of mass should be L over 2. And the reason why I point that out is because there's going to be a force of gravity equal to the weight, which is equal to mg, that's actually acting on that rod. And that's really the only thing acting on it. What I would like to do is find the angular acceleration of the rod just after we let it go. So you can imagine this rod's being held up, and then I'm going to let go of it, and immediately it's going to start falling. And what I would like to know is the angular acceleration of the rod at the moment of release. And then B, I want to know the linear acceleration of the tip of the rod at the moment of release. So I'm going to say, what is alpha at t equals 0 when the end is let go? And then in part B, what is A for the end? Okay. So when I say A for the end, I mean this end right here. I want to know what that acceleration is. Now, the reason why I want to do that is I want you to think if you just drop this thing, it would fall at g, 9.8 meters per second per second. This thing's actually going to make a speed that changes as a function of time, but initially it's going to take off with a different acceleration than g, and I think you're going to be surprised at how big the acceleration is. So let's begin. What we can do is we set up our summation of the forces. So here's our solution. We're going to set up our summation of the torques is equal to I times alpha. This is a rod. Let me see if it says. Yeah, I'm going to assume the dimensions of the rod aren't that big and that sort of stuff so that we can go ahead and calculate what I would be. But I actually did this on one of the videos, but I can mention it again now. But I, for a rod about the end, is equal to 1/3 ml squared. That's the moment of inertia. So we have that, uh, and that's about it. So what we know about what we've been learning in chapters 9, 10, and 11, well, we haven't started reading 11 yet, but at least chapters 9 and 10, we learned that the laws of physics are sort of the same. They don't change when we go from point particles to physical bodies. But what we did find is that the laws of physics in the universe behave in such a way that it seems, at least, all the forces are acting on these bodies at their center of mass. So that's why I drew W equals mg at that little dot that's L over 2 from the left hand side, because that is the geometric center of this. And if it's a uniform rod, the geometric center should be the center of mass. So, with that being said, let's go ahead and write down everything we have. We're ignoring friction, so there should be no torque for that. And all I have then is just the torque due to the weight. That torque is tending to cause a clockwise rotation, which I would normally call negative, but we're just dealing with magnitudes here, so I'll just call it positive. Okay. So I'm going to say the summation of the torques is going to be M times G times L over 2. Now remember, the formula for torque is R times F times the sine of theta, but it could also be R perpendicular times F, and it can also be F perpendicular times R, and it could also be torque is equal to R cross F. In this case, I really just have a lever arm, which is this R vector, and it's automatically at 90 degrees. Okay. Again, notice how it should come from the center of that. But if this whole distance is negligible, that half distance is negligible too. So we've got our torque equal to force times distance. The angle is 90 degrees, so the sine of 90 is 1. We've got that. That's literally the only torque acting on it. Now, on the other side, we've got 1/3 ml squared, as our moment of inertia. So I'm going to write 1/3 m times L squared. That's my moment of inertia. And then my alpha is the angular acceleration. What we would like to find in part A is alpha. So I can automatically see right now that this exponent of 2 is going to become 1 and this L is going to disappear. I can also see that this capital M is going to disappear. And now I can say that alpha, the angular acceleration of the rod, is in fact going to be equal to 3g over 2l. And that's actually the result. So notice this acceleration. Uh, well, you can't tell much with this, but once I do the linear acceleration, it'll make sense. Anybody have any questions on how I got that so far? Now, technically speaking, as this thing fell, the angle between the lever arm and the mg force is going to change from 90. It's going to get bigger. And that's going to make the torque a function of time, a function of theta, all sorts of stuff. And that's going to make the acceleration a function of time, a function of theta, and all sorts of stuff. So it's not one we can readily solve, but we can solve for it at the instant it takes off. And that's what we just did. Now, since we have S is equal to R times theta, we can also use this to get V equals R times omega and A equals R times alpha. So now I'm going to use A is equal to R times alpha to realize that the acceleration at the tip is equivalent to having a radius of a whole length L. So I'm going to say A is equal to L times alpha, which is equal to L times 3G over 2L. You can see the L's cancel out, and that gives me A is equal to 3 halves G. So 3 halves G means 1.5 times gravitational acceleration. So that should warn you that, like, if you ever happen to be somewhere where you're working with some friends, you're trying to cut down a tree, that sort of thing, just be advised that the tip of the tree is going to fall way faster than you're used to because the end of it is not where the force is acting. The force is acting at the center of mass, and that is going to tend to try to rotate and fall in such a way that it's in some sense 9.8 meters per second per second. But this one is going to go more or less twice as fast, and therefore it's not going to be as predictable as you expect. It could actually be, quite devastating. I suspect this is the reason why anybody gets killed by trees, other than just not paying attention. If you actually watch a tree falling, they don't fall fast enough for you necessarily to not get out of the way. But if you expect it to go one speed because you're used to how fast things fall and it goes quite a bit faster, you can get caught and get hit. So, anyways, take that as a warning. That also happens to be, for instance, if you ever see anybody knock over a tower like a smokestack or a silo or something like that, you almost always see when it starts to fall, it'll break in half. The reason it breaks in half is because it's not meant to handle multiples of G forces. And that's what's happening. It's trying to accelerate way faster than G, at least above the center of mass. And it's not been designed to withstand that kind of acceleration. That would be the acceleration that you get like in a 10.2 magnitude earthquake. And they don't have to design to that spec. So when it starts to fall, the top half will break loose because it just can't keep up with the forces that are hitting it. Any questions on that before we move on? All right. I can show you rather quickly how to calculate a moment of inertia, and I think that's a worthwhile thing to do. So let me start off with a rod. So the formula for the moment of inertia is I is equal to the integral of r squared dm. Uh, what we could do is we can imagine, for instance, putting a coordinate system right here This would be my x-axis. This would be my y-axis. You really don't even need the coordinate system. It just gives me a way to reference it. But what we're going to do is take an actual object and center it up on this coordinate system and rotate it about the y-axis. So I'm going to imagine that this dimension is very small. And I'm also going to imagine that the dimension in and out of the page is equally small. It's really, really, really teeny. Okay. What I want to do is calculate the moment of inertia as it rotates about that axis. Now, I am going to say that this end is at L over 2 and that this end is at negative L over 2. And what I'm going to do is choose this little sliver right here. That's going to be my differential mass element. So I told you guys when I first introduced the center of mass and then when I introduced the moment of inertia that dm can be equal to lambda times dl, or it can be equal to a sigma times a dA, a differential area element, or it can be equal to a rho times a dV, which is a differential volume element. I'm going to use dm is equal to, this looks like one dimensional, so I'm going to use dm is equal to lambda times d. Notice it's along the x-axis, so it's smart to just call dl dx. All right. I'm going to say this rod has a mass m and a length L. And I'm going to tell you that the rod is uniform, has its mass uniformly distributed. Because of that, we know that lambda is a constant. That's what uniformly distributed means. It means on a linear object like this one, it means lambda is a constant. If it's a two-dimensional object, it means sigma is a constant. That's the number of grams per square centimeter. And if it's a three-dimensional object, rho is a constant. That means the number of grams or kilograms per cubic centimeter or per cubic meter. Okay. So, in fact, just so you understand, lambda is going to have to be equal to m over L for this guy, but I'm not even going to necessarily need, well, we'll see. I might not need it. I might need it. But anyways, that's what lambda is going to be. And not only that, the distance r away from the axis, that distance r is actually equal to x. So I'm going to go ahead and do my solution. And this is about the center. So I is equal to the integral of r squared dm. That becomes the integral from x equals negative L over 2 to L over 2 of r, which we replaced with x. So that'd be x squared times lambda dx. And that lambda can come out in front. Oops. Lambda can come out in front, don't need an underline, times the integral of x squared dx from negative L over 2 to L over 2. Now the integral of x squared is 1/3 x cubed, so I'm going to say this is lambda over 3 times now L over 2 cubed minus negative L over 2 cubed. Everybody follow what I did there? I had to substitute in the L over 2 for each of the ranges of integration, and they have to be put in parentheses. That's a big thing to make sure you don't miss. In the case of L, negative L over 2 being cubed, that's going to ultimately result in a negative. So what's going to happen is this minus a negative becomes plus a positive, and we get L cubed over 8 plus L cubed over 8, which is 2L cubed over 8. So now I can say lambda over 3 times 2L cubed over 8 is what our value is. I can obviously cancel out that 2 and leave a 1 and cancel out this 8 and leave a 4. That'll be fine. And now I can go ahead and say I is equal to 3 times 4 is 12, so this is going to be 1/12 lambda L cubed. Now I'm going to plug in what lambda is. If we were doing a center of mass calculation, the lambda would have canceled out. I'm going to put in what the lambda is. So we got 1/12. The lambda is m over L, and then it's times L cubed. So finally we get I about the center. This is for a rod uh, rotated about its center. Turns out to be 1/12 m L squared. And if you look in the table that you have in your textbook, you'll see that's exactly the right answer. If we wanted to do about the left end, we could do that as well. So let me show you that one. Now let's see. What is I if rotated, excuse me, about the left end? So in this case, I'm picturing my rod like this, and the length here is L. The axis of rotation is that. What I'm going to do is take a little differential area, or excuse me, a differential mass element. dm is equal to lambda dx. And I'm going to notice that this distance from here to here is r, but it's also the variable x. So I'm going to do that. So now I can say solution I equals the integral r squared dm. And I also should say the parallel axis theorem says the moment of inertia about a parallel axis is equal to the moment of inertia through the center of mass plus m times b squared, where b is the distance between the center of mass and the new axis. So I'm going to show you both ways. Let's do I is equal to the integral r squared dm. We know that it becomes the integral of x squared times lambda times dx, but this time we're integrating from x equals 0 to L. I'm going to go ahead and plug in what lambda is just to make it easy since we saw that we had to have it anyways. So I'm pulling that out in front, and now I'm integrating from 0 to L of x squared dx. That's going to give me m over L times 1/3. Now we're doing L and 0, so that's just going to become 1/3 L cubed minus 1/3 0 cubed, but that's just 0. So now we can see that the I about the end instead of the center of mass is actually equal to 1/3 ml squared, and that's the right answer, which you can also tell from the table. But the other thing is we can use the parallel axis theorem, and through a parallel axis, it should be equal to 1/12 ml squared, because that's what we found when we actually rotated about the midway point right through the center of mass. But now I have to take that mass and multiply it by the distance between the center of mass, which was at L over 2, and the end. So that distance is L over 2, and I just got to square it. That's what the parallel axis theorem says. So now I get 1/12 ml squared plus 1/4 ml squared, because obviously 1 over 2 squared becomes 1/4. Now that's the same thing as 3/12 plus 1/12, so that'd be 4/12 ml squared, which equals 1/3 ml squared. So now we have the moment of inertia for a rod about its center and for a rod about its end. That's enough for today. As I said, I'm going to put some more videos up. We're trying to play a little catch up here. I'm just trying to knock out chapter 11 and I'll finish chapter 10 first, and then I'll do chapter 11. Again, 11, 14, and 15 are going to be sparsely covered just because of the time constraints that I ran into. And don't worry, I will do my best to make sure I don't, stiff you guys. I'll be fair. Don't worry. If something turns out that you guys don't do as well as I expect, I know the part of it that I play, so I'll make sure I take care of you. Don't stress too bad, but do try to continue doing your homeworks. Knock out chapter 10. 11, 14, and 15 might turn out to be extra credit homeworks, but they're definitely going to be on the final exam and the final test. So you guys are free to go. I'll wait for the last person to leave in case anybody has any questions, but thanks for coming, and we'll see you again later. How's it going, Claire? Chloe? You have a
Hey, how are
question?
you doing? Oh, I don't think my camera's not gonna work. Can you hear me okay?
Yes, I hear you.
Okay. Okay. I was just checking to see if it was still okay to make up that one face-to-face exam we talked about. I had made a mistake and did the practice one instead of the original.
Gotcha. Yeah, yeah, it's not a problem. When did you say you want to do it?
I'd be able to do it anytime this week. I did try to reach out to the testing center to try to do it tomorrow.
Okay.
Um, oh, sorry, but um, if you're able to send a proctoring request, I'm not sure.
Yes,
But
I can do that. In fact, I've already sort of sent one for one thing that they might interpret it good enough for because I told them I said I had some students, but I don't know their names. So that might
okay.
actually work. But I can submit another one. Do you think you're going to be able to go there tomorrow, or did you get an appointment for tomorrow?
I sent a message out last night, and then let's see, the last email I got from them said um so I said I was gonna be reaching out to you for a proctor request as well, and they said is that they haven't received anything. They
Okay.
didn't really, yeah.
Gotcha. Well, I'll go ahead and submit it, and I'll leave it for tomorrow and Wednesday and Thursday just in case.
Okay, okay, I really appreciate it. Thank you so much.
No problem. Have a good one, Chloe. Bye
All
bye.
right, you too. Bye.
Okay. So it looks like it's about it, and I'm going to say bye bye. Bye bye.